Oh, okay. I'm glad you went there with that. Well, not really, but it was better than what I thought you were going to say. Ice picks make. I don't know. I don't know. I don't know. Right? You know, I told you earlier that I commit crimes in the evening instead of going to sleep, and then you're talking about an ice pick makes the best, and I'm just filling in the blanks there. Um, Murder weapon. Right. Oh yeah, at Ravensdean Park. Yeah, yeah. Okay. You got to be careful though with that. I mean, that can. That was a joke. Oh, that's right. You can. I was gonna say you can give yourself one with that. Yeah. Okay, good. I'm glad you're just joking. Uh, I won't fill out that counselor request form for you then later. Okay. So example 6, starting at example 6, if we use direct substitution and we get one of these two forms, okay? These are called indeterminate forms. Indeterminate forms, okay? That means that from that number, you cannot, in general, determine the limit, okay? You have to do something else. You have to either go to a numeric device like a calculator and punch some numbers, you know, to evaluate it, or you use a computer, or there's some algebraic methods that we're going to learn. And then the answer may be 5, or it may be negative 13, or it still may be undefined, DNE, infinity. You don't know. Okay? We've already seen several examples like infinity over infinity when they're both growing. It depends how fast one is growing with respect to the other. And sometimes it's 0, sometimes it's leading coefficient over leading coefficient, and sometimes it's infinity. But it basically means we got to roll up our sleeves and do something else. And so if you already come with your sleeves rolled up, that'll save some time. We're going to learn some algebraic methods. And I give each method a name. You do not have to know the names, but it does help to maybe recall the algebraic method, because what you're responsible for is when you get direct substitution and you hit one of these two, based upon how the equation looks, you have to know what to do, okay? And the first method we've already done. We've quizzed over it. It's the factor and divide out method, or what I call the FADO method, or FADO. I don't know if I wanted to say long A or short A. I'm still thinking about that. Because if I say FADO, people just think, oh, it's just a passing trend. But no, it's not. It works. FADO, 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 FADO. There you go. We'll call it the FADO method. I like it. Brilliant. Well, they teach you that in like ROTC? How to do that? It's just a gift. FADO. I'm going to call it FADO. That's not FADO or FADO. FADO. I like it. We've already seen this method. It works well when you have rational functions. Okay. Polynomial over polynomial. Polynomial over polynomial. You plug in a number and you get 0 over 0. The factor theorem says x minus that number that you plugged in is a factor of that polynomial. So if you plug it in, you get 0 over 0. You factor the top as x minus the number. You factor the bottom as x minus the number. You divide it out and you plug into what's left, right? For example, A. Plug in a 2 and you get 0 over 0. Now it's good to get in the habit of writing 0 over 0 kind of up here above the equal sign. It shows me that you've actually tried direct substitution first, and later on when we learn advanced techniques called L'Hopital's rule, which I taught last year to the AB class on after school and weekends. Anyway, long story. Why did y'all bring that up? What? No, it's okay. This is going to be a very important thing to show. Okay, so let's go ahead and do it. The top is a difference of squares, and it factors into x minus the number we plugged in, and you can use that to help you figure out the other one if you're not sure. But that was easy, all over x minus 2. Now, you don't need parentheses around the x minus 2 in the denominator, do you? Like that? But when you're dividing out, you want to go ahead and group it together. So now when you swipe through it, you know the whole thing's gone, and not just like the 2 in the bottom is gone, and you're left with x minus. Make sense? Okay, and so now that graph behaves just like the line x plus 2, except it's got a hole at x equals 2. So we can use the graph of x plus 2, which paves right over the hole. By direct substitution, we get 4. Okay, and that would be the notation as well. this came up on the Facebook group page the other day about how much notation we need to show. And there were like other teachers that were like, can you show this, or this, which is less notation? And pretty much unanimously, the answer was no. So if you work straight down, until you plug in, you need the limit in front. Once you plug in, which is after you eradicate the 0 over 0 or infinity over infinity, which I call that the bad guy factor. We can just get that out of the way. We call this the bad guy factor. He's the factor that's causing the 0 over 0 or infinity over infinity. It's like over the weekend, I don't know if you heard, but like supposedly the U.S. government took out Osama bin Laden's son over the weekend. And by took out, I don't mean like, went to a movie with him and said, would you like some popcorn? They killed him. I don't know what his name was. It was like, you know, what? Hassan bin Laden. I was thinking like Delirious bin Laden, but Hassan bin Laden. Yeah, they got him. So just like the U.S. government, we're trying to eliminate the bad guy, okay? So that we can make the world safe again for not democracy, but direct substitution, okay? Everything leads back to direct substitution, okay? All right. Hassan bin Laden. Did you know that? You follow the bin Ladens pretty closely on Facebook? Yeah? Okay. All right. Yeah. Yeah. I heard it on the news this morning and I didn't really, they didn't repeat his first name, and you're like, what was that? So, okay. Letter B, let's try it. Never not first. What do we do? Direct sub. Let's plug in a 1. 1 cubed minus 1 is 0 over 1 minus 1 is 0. Hot diggity dog. So, because it's a quotient of two polynomials, I know that 1 is a 0 or a root of both of those polynomials. So I know x minus 1 is a factor of, bless you, each of those polynomials. And so I know I'm going to be able to write it like that. Bless you. And then I'm going to eventually, or I could do it now, what the heck? I could divide out the bad guy factors now, but what do I need? I need the other factor. So what do you get when you factor out an x minus 1 from an x cubed minus 1? Is it x plus 1? If that were x squared minus 1, it would be a difference of squares. This is a difference of two perfect cubes. Raise your hand if you know the formula for the difference of two perfect cubes. Notice my hand didn't go up either. That's okay. Right? Yeah, I don't know it. But here's what. You don't need to know it because you could just lean in carefully, and just listen to what that little symbol is telling you, right? We've heard this before. What is he saying? Divide me. So you can either do long division, okay, like we did earlier when we found slant polynomials or slant asymptotes, or because you're dividing by a linear factor, that's an x to the first, you can do it synthetically, okay? So let me teach you synthetic division or synthetic substitution, okay? It's a little bit faster, a little bit slicker than long division, but long division would still work, okay? So here we go. You write out the coefficients of the numerator in descending order. So I have a 1x cubed, and if you remember, you need a placeholder for missing terms. That's hugely important. So that would be 1x cubed, 0x squared, 0x, and then we're back to a negative 1. You always synthetically divide with the root instead of the factor, right? You divide with the factor, x minus 1. You synthetically divide with the root. That's basically the number you were plugging in. All right, so you set it up like that. Now here's what happens. This last box underneath that number, this is going to be the remainder. Okay, but it's also going to be the function value. All right, and for us, because we've already plugged in and got 0, we know that should be 0. You don't have to fill that in right now, but I'm just kind of reminding you. So here's how we start the process. It's real easy. Just let gravity do its thing. Just bring it down. Okay, just bring down that first number every time. Now you multiply along the bottom and you slide it up and then add. Okay, multiply, slide it up to the next column, then add. So 1 times 1 is 1, slide it up, you add, you get 1. Multiply, you get 1, slide it up, add, you get 1, boom, you get 0. Okay, so these are the numbers down here that we really are after. These are the coefficients of the quotient, which is 1 degree smaller. So if we started with an x cubed, this would be 1x squared plus 1x plus 1. Yeah, those are the coefficients. So it's a little bit faster than long division. 1x squared plus 1x plus 1. There we go. And now I could just plug that 1 into what's left. And I get 1 plus 1 plus 1, which is 3. And remember, when you plug in, you don't need to write the limit anymore. What if you mess up and you still put the limit here in front of the 3? Is that your final answer? That would not be your final answer because you still haven't evaluated the limit as x goes to 1 of 3, which would be 3. The limit of a constant is a constant because it's just a horizontal line. So don't do that. Okay, and don't do this. Some people do this. The limit as x goes to 1 equals. What's wrong with that? Yeah, there's nothing here. The limit as x goes to 1 of what? Of what? Peaches? No, I don't know. Okay, you don't give yourself a road to drive on, right? I don't know. Yeah, don't do that. Just work straight down. You don't even need equal signs. Okay, good? You got it? All right. Example C. Oh, the limit as x goes to -1 of that polynomial over that polynomial. Never not first direct substitution. Let me save you some time. You will get 0 over 0. If you want to verify that at home tonight, go ahead. Now, I want you to do this one on your own. Always practice proper notation. Don't let yourself off the hook. -1, yeah. Yeah. It's the number you're going to be approaching. Yeah. Yeah, like if you had this function here and you wanted to evaluate it at -1, you could just do synthetic division, and that last box is the function value. If you wanted to evaluate it at 5 or something, that's how computers do it, because 5 to the 4th gets really big really fast, whereas synthetic substitution is just additions and multiplication. So it comes from nested form. Mm-hmm. Let me see, I haven't done it yet. 1x to the 4th, -1, -3, -4, and -1. Move this out of the way. Okay, gravity, right? Boom. Now you multiply this times that. And then you add. You should get 0 in that last box. Uh-oh. Oh, -1 plus 2 is +1, not -1. Yep. All right. So if you know that since I told you it was 0 over 0, you could have verified that yourself. Because -1 then is a root or 0, then x minus -1 or x plus 1 is a factor. Those are the bad guy factors. That's what you're trying to get rid of. So you ultimately need the other two factors. The bottom is pretty easy. You can always figure it out. If this is x and you need a 2x squared, that has to be a 2x. And if that's a 1 and it needs to be a -3, that has to be a -3. And then you can verify the product of the inner and outer. -3 plus 2 is -1. That's what pre-cal's doing right now, reviewing factoring like that. But the one up here, that's a lot harder unless you use long division. So synthetic division a little bit faster. We don't need a placeholder. Everything's there. Bring it down. Multiply, add, multiply, add, multiply, add. You should get a 0 in that last box if you've already used direct substitution and got a 0. So remember, these are what we're after. That's the distilled product right there. So if we started with the 4th degree and we divided out a linear factor, then that's the coefficient of the polynomial that's 1 degree smaller, okay? Sometimes we call it a depressed polynomial because, well, not because it's in a math class and it's sad, but because it's 1 degree smaller, yeah. So that would be a 1x cubed, or cubed minus 2x squared plus 1x minus 4. So I don't know if you'll have anything that daunting on the AP exam, but it's nice to know that if you ever need to quickly divide out a known factor because you know the root, synthetic division will give you the other factor. And of course, that's helpful for us because now we can use direct substitution and we get -1, -2, -1, -4, all out -2, -3. Is that a good place to stop on a free response? Sure is. And I think it's equal to some number. I think it's alive, right? What is it? -3, -4, -8, a -5. You could stop there. You can call it 8/5. You can call it 1.6 if you want. That's it. Yeah, not bad. So synthetic division. After we get 0 over 0, if we recognize it as a polynomial over polynomial. So again, a polynomial is just your exponents on your x's or variable, whatever it is, are whole numbers, 0, 1, 2, 3, 4, 5, 6. They're not fractions. They're not negative. Okay, they're the nice looking ones. Okay, any questions on that? Review with a little bit of a stretch there, right? Synthetic division thrown in. All right, this one here, we actually learned this method today in pre-cal, just for the case of rationalizing an expression. It's going to become an algebraic way for y'all to eradicate the bad guy. I call it Ratcon, which is short for rationalization conjugation. Rationalization conjugation, or Ratcon for short. So it's going to work well when you get 0 over 0 and you have something that looks like this. Namely, you have two terms where at least one of them has a radical. They could both be radicals, like the square root of x plus 1 minus the square root of x minus 2, blah, blah, blah. And those two terms could be either in the numerator or the denominator. It doesn't matter. So remember, what it means to rationalize an expression simply is to get the radical to the other side of the fraction. That's all it means. If it's in the top, we're going to get it to the bottom. If it's in the bottom, we're going to give it to the top. And because there's two terms, we accomplish the goal by multiplying by the conjugate over the conjugate, which means all we do is we change the middle sign. That's it. So let's take a look at example 7a. The limit as x goes to 0, so it's a limit alert. We plug in a 0 for x, and we get the square root of 1, which is 1, minus 1 is 0 over 0. Okay. Now, it is always good to identify the bad guy factor before you even start, right? Lest you have collateral damage. You don't want that, right? So in the bottom, it's the x factor itself that's causing the 0. So I look in the top, and I'm like, ooh, there's two terms. Can I factor an x out of both of those so that I can divide it out? No, I can't. So the factor and dividing out process did not work. But what can I do? Well, I notice that there's a radical, and it's two terms. So I'm going to multiply by the conjugate, the square root of x plus 1 over itself. And you can just add it in there like that. I'm just multiplying by a clever form of 1. Now, as we work down, of course, I'm going to expand the numerator, because by design, the product of two conjugates gives you a difference of squares. Okay? So let's see what happens. Radical times radical is radicand, x plus 1. And I'm putting parentheses around it just to show the grouping, that it came from the radical underneath the radical. But there's really nothing to distribute. Now, here's the cool part that you could just verify in your head. Your inner is minus radical. Your outer is plus the same radical. Those are opposites. They give you a 0. And so then the last would be -1 times +1, which is -1. Okay, so the radical's gone from the top. In the bottom, you're going to leave it factored. Don't distribute the x. Why? He is the bad guy factor. And if you distribute him, you're going to let him run underground. And you might not be able to get him back, right? You're going to have to extract him again. You can only divide out common factors. Sorry. You can only divide out common factors. So leave him factored here. Now, in the top, what should we do? This is where some people get kind of lost. It's good to have the parentheses to show that it came from the radical, but do we really need them here after all? Is there anything to multiply through or distribute or expand? No. So in the words of Reagan, tear down this wall. Hey, look at that. Now Germany is united. Yeah. 1 minus 1, you can combine like terms now, and that cancels to give you 0, right? And once those are gone, and only once those are gone, now what can we do? Divide out the x's, leaving a what? A 1. And you could do both of those in the same line if you want to, as long as you promise me that you cancel the 1s before you divided out the x's, because I can't tell. And if you did it the other way around, I'm going to be mad, okay, because it doesn't work that way. Now, since the x over x is eradicated, what can we do once we get rid of the 0 over 0 problem? Plug in, okay? Everything leads back to direct substitution. So I have a 1 over, and that'll be the square root of 1, which is 1 plus 1 is 2. So we get a half, okay? So whatever the function looks like, that original expression or that original function, it has a hole at the point 0, 1/2, yes? There's a hole at 0, 1/2. That's the limit from the left of 0. That's the limit from the right of 0. Ratcon. When do we use Ratcon? Not when we have rats, but when you have radicals and at least 2 terms, right? 2 terms. That's where the con comes in. All right, so go ahead and try B on your own. Never not first, though. If you plugged in first and you got 7, that's your answer. You wouldn't need to waste all that time Ratconning it. But that's not the case here. Again, practice proper punctuation, if you will, notation. Bring your limit down each time until you're ready to evaluate. Mm-hmm. They're laughing next door, having fun. Put parentheses around here, x minus 3. It should be there in the top already. The bottom is where you really need them. There you go. Because that one would lose points in the top.
There's nothing else on the bottom.
Oh, you don't need them really in the bottom. I like you to have them there.
I was going to get into the top.
Yeah. Okay. Yeah, that's fine. What'd you get, Cam? What'd you get? No. You got no? Is that like another version of D&E? Speaking of D&E, you got to keep your mind wrapped around what it is you're finding. If you plug in and get 0 over 0, don't just put D&E because we're finding the limit. What is D&E though if you get 0 over 0? The function value, right? But we're finding the limit. So 99 times out of 100, 0 over 0 means there's a hole. You got to find the limit. So in this case, you do Ratcon. You multiply the bottom out, and you get x plus 2 minus 5. And now those parentheses could obscure your view. But remember, tear down the walls. That's x minus 3. You can actually group it and divide the whole thing out, And then you get the square root of 5 plus the square root of 5, which is 2 square root of 5. And that's your answer. So 2 square root of 5. It's square root of 5 plus the square root of 5. Hey, be working on worksheet 1.4 because it's a fun one. It's a good one. Yeah, we'll see you tomorrow. Have a splendid afternoon.